Hello everyone. Today I'm going to give a brief introduction of our current work on selective context-sensitivity for k-CFA with context-free language reachability. Pointer analysis solves the point-to relations between pointers and objects in a program. It's the cornerstone of most static program analysis, such as tent analysis and type state analysis. Context sensitivity is important for a precise point analysis. For example, we have an identity function m which returns whatever it receives. A context-insensitive point analysis uses a single abstraction for variable n. As the analysis cannot filter out unrealizable paths, the parameters and return values of the two calls to m are conflated. On the other hand, a context-sensitive point analysis will distinguish the two calling contexts of M, proving that the two calls can actually return two distinct objects. Despite improving precision, a context-sensitive analysis must take into account all the calling contexts. K-limiting context-sensitive point analysis, which limits the length of each calling context to K, still suffers from the context explosion problem, making it difficult to increase its precision by increasing K. With the desired precision, the increase in time and space consumption is disproportionate. In other words, it is difficult to obtain acceptable precision within the allowable time and space consumption. A series of recent studies have proved that not all contexts can benefit to precision. A considerable part of the context does not contribute to the improvement of precision. Therefore, how to selectively apply context sensitivity has become a topic. To make such selections, a pre-analysis is performed to determine heuristically whether a context should be ended or not. Different heuristics are used, including user-supplied hints, pattern matching, and client-specific machine learning techniques. This time, we want to discuss it from a very basic perspective. In the example above, we can see that whether n is context-sensitive or not ultimately affects the precision of the points-to-information computed for V1 and V2. However, n is neither V1 nor V2, and in real-world applications, they can be far away from each other with complex field accesses via a long sequence of method calls. How do we know that making n context-sensitive can avoid some spurious points-to-relations? We may attempt to resort to some heuristic-based rules regarding, for example, the alias relations between n and V1 or V2. However, such rules often don't admit a quantitative analysis of their sufficiency and necessity. In many cases, the effects of these rules on the efficiency and precision of context-sensitive analysis are unpredictable and often unsatisfactory. Here, let's discuss the necessity of context sensitivity from a very basic perspective. In general, if a point-to-relation holds in a point analysis, then it will also hold in the less precise point analysis. Conversely, if a point-to-relation does not hold in a point analysis, then it will also not hold in a more precise point analysis. Of course, the more precise or less precise mentioned here refers to strictly more precise or less precise. Strictly, it doesn't mean more or less, but means inclusively. That is not to say one part is more precise and the other part is less precise, and together is more precise. This is not the case. This requires that the two-point analysis being compared should be compatible. For example, a one-cosine sensitive analysis and a two-cosine sensitive analysis are compatible. Naturally, if we change a single point n in a context-sensitive point analysis to context-insensitive, then this modified point analysis should still be compatible and equal or less precise than the original one. Thus, we can write out the necessary and sufficient conditions for context sensitivity based on this. That is, there exists a pair of object and variable. There is no point-to relation between them in a context-sensitive point analysis, but the point-to relation holds in the variation where a single point n in the point analysis is context-insensitive. Then n must be context-sensitive to avoid such spurious facts. This looks a little trivial because the verification will include a k-context-sensitive point analysis. Not only that, we also even need many single-point context-insensitive variations, once for each single node in the program. In our work, we exploit context-free language reachability to develop a necessary condition that is efficiently verifiable in order to approximate conservatively the set of variables or objects that require context sensitivity. This allows us to develop a faster pre-analysis to verify context sensitivity for each node in the program. Context-free language reachability, which is an extension of standard graph reachability, can be used to formulate a point analysis that operates on a graph representation of the statements in the program. By using back propagation, it's able to express all point-to relations by explicitly concatenating the original statements, also known as terminals in the language. For example, a typical failed access can be expressed as a balanced parenthesis of store and load, connected with alias, founded by a backward flow followed by a forward flow. Context-sensitive value flows can be expressed as a balanced parenthesis matching problem too. For previous example, the matching of the call sites ensures the value flows across different call sites do not get conflated. A field-sensitive and context-sensitive point analysis is often expressed as the intersection of these two. We leverage such a dichotomy to develop our approach. With the context-free language tool, we can recast original condition to its context-free language version. To decide context sensitivity of a node n in the program, there should exist a context-free language path from some O to V passing by n, such that it satisfies the field language, and it doesn't satisfy the context language, but both of the two subpaths divided by n satisfy the context language. This will be very easy to understand if compared to the original conditions. First of all, condition 2 says that the path is not context-sensitively reachable, which ensures V does not point to O in a context-sensitive point analysis. And at the same time, both of its two subpaths are context-sensitively reachable, which makes the single point n the only context-insensitive node. Condition 1 plus condition 3 corresponds to the latter one in the original condition. That is, V points to O in a context-sensitive point analysis where n is the only node analyzed context-insensitively. Compared to the original sufficient and necessary condition, there will be a little bit over-approximation, as the relationship between the context-free language path and the points to is not a one-to-one mapping. But for most cases, this condition is tight enough. This condition is just a tight transformation of the original expression and does not change the complexity. To enable this condition to be verified, we need to simplify it. As we talked about earlier, a field-sensitive and context-sensitive point analysis is often expressed as the intersection of two context-free languages. We can simplify it by leveraging such a dichotomy. We over-approximate the language by regularizing the field language. The context language is kept so as to keep much context information as possible. Correspondingly, the condition for context sensitivity is relaxed to the version where the field language is replaced with the regular one. Then, what's the over-approximation? Let's illustrate this by using the example given here, which is slightly modified from the previous example. M is still an identity function, but returns a wrapper this time. In this example, N can be context-insensitive if following the original or context-free language condition, except that there are some use of the field F of V1 or V2. These cases should be recognized by the original or context-free language condition. But N must be context-sensitive conservatively if following the simplified condition, even there are no use of field F yet, as it can easily find such a path under its own criteria. To evaluate our approach, we use 11 popular programs, including some from commonly used Java benchmark suite and several classic applications. We have evaluated our approach on k-CFA-sensitive point analysis for demonstration. In order to demonstrate the comprehensive utility, the results are normalized according to the baselines. For the precision, it's obtained from the false positives reduced from the corresponding context-insensitive point analysis, taking the number for two cosine-sensitive point analysis as the unit length. Times were also normalized so it ranges from 0 to 1. The one that is lower is more efficient, and the one that is further to the right is more precise. Context-insensitive point analysis and two cosine-sensitive point analysis spot at 0, 0, and 1, 1 respectively. The blue dots represent the analysis guided by our approach for all 11 evaluated benchmarks, which clearly show its effectiveness. That's all. Thanks for watching.